The solar corona is the outermost layer of the sun. It's always there, but not bright enough for us to see in the sky, except during a total solar eclipse. Only as we stand in the moon's shadow can we see the pearly white light of the sun's corona in all its glory. I'm Dr. Sherilyn Morrow, leader of the Public Engagement Program embedded within the NASA Punch mission. I'm joined by the overall mission leader, Dr. Craig DeForest.
Hello, good to be here.
And also by Punch project scientist, Dr. Sarah Gibson.
Hi.
The corona is a scientific marvel. It accelerates outward in all directions from the sun, becoming the solar wind. This constant stream of star stuff fills our entire solar system.
Yes, and the solar wind is so faint and so sparse that it's very close to being nothing at all. Yet it carries solar storms and other forms of space weather that affect the Earth and all the other planets.
The previous episode of Science Through Shadows featured the Parker Solar Probe. Parker is a mission to touch the sun because it flies within the solar corona. In this episode, we focus on a sister NASA mission called Punch, which is composed of 4 Earth-orbiting spacecraft. Each satellite carries a camera that peers out into the solar wind to provide a big picture view of how the sun touches us.
The solar corona is mysteriously hotter than the layers beneath it. It is so hot that it can't be held down by the sun's gravity, and it continuously escapes as the solar wind. The Punch and Parker missions both observe this transition, but from different perspectives.
In December 2024, Parker made its deepest and fastest of many dives into the outer solar corona. During one close approach, Parker flew through a solar storm just as the storm was being ejected from the sun.
Yeah, Parker is awesome. And the Punch mission has a few superpowers, too. Not only does it study this important transition from the corona to the solar wind, but it's also capable of tracking how the solar wind changes and evolves as it heads farther away from the sun.
The solar wind is really different from winds on Earth because it is a continuous flow of electrically charged particles that race away from the sun in all directions. Comets are like the windsocks of the solar wind. Comet tails are stretched away from the sun by the solar wind outflow.
In the early 1960s, a NASA spacecraft near Venus made the first direct measurement of the particle outflow of the solar wind.
And now, the 4 Punch spacecraft, working together, can create large-scale images and movies of the solar wind.
Although the solar wind extends far beyond the orbit of Pluto, Punch focuses on the solar wind of the inner heliosphere. This is the 3D volume of space between the outer corona, where Parker flies, and the orbit of Earth around the sun.
This is the entire inner solar system, a volume of space so vast that it could hold 1 million suns or 1 trillion Earths. And Punch can observe this all at once. But most people think this space is pretty empty except for the inner planets.
Well, the particle density of the solar wind is outrageously low. On Earth at sea level, a volume of air about the size of a sugar cube contains millions of trillions of atoms and molecules. But in the solar wind, that same volume would contain just 1 to 10 atoms or electrons. No vacuum chamber on Earth can even come close to achieving that void.
This means that the solar wind is so sparse that no particle ever hits another.
But because all the particles are electrically charged, they interact at a distance through the electric and magnetic fields. That makes the wind work like a fluid, with surges, turbulence, and eddies that the Punch cameras can observe.
That's right, Punch can track solar storms and other solar wind structures because of the way sunlight is polarized by its interaction with the particles of the solar wind. And it's this polarization measurement that allows our science team to pinpoint the location of solar wind features in 3D space. I like to call it localization by polarization.
So, for example, using polarization measurements, Punch can follow the behavior of solar storms called coronal mass ejections, or CMEs for short.
Punch makes it possible to track how CMEs are moving and changing as they expand into the solar system. Punch observations may help to spark a revolution in space weather monitoring, akin to the way Earth-observing satellites revolutionized hurricane tracking on Earth.
Of course, most CMEs miss the Earth, but when solar storms do come our way, there's a risk of harm to astronauts and satellites in space.
There is also the potential for incredible beauty.
CMEs interacting with Earth's magnetic field lead to the dance of the auroral lights.
To do the big science of tracking and studying space weather, the Punch mission uses 4 small, suitcase-sized spacecraft that launch together on a single rocket and spread out in low Earth orbit. Each satellite carries its own camera aimed outward into the solar wind.
One of the spacecraft has the nickname Unify, which is short for Narrow Field Imager. Unify is a coronagraph that uses an occulting disk to shade its camera from the brightest parts of the sun. This allows observation of the outer corona, where the solar wind and solar storms begin.
And the other 3 Punch spacecraft are called Wiffies because they each carry a wide field imager with a field of view about as large as a high-quality mobile phone camera.
The Punch cameras are able to make images of the super faint solar wind, even while the bright light of the sun shines on the spacecraft.
Our Punch engineers accomplished the feat by designing a set of baffles that cast very deep shadows on the filter wheel and camera within each spacecraft. Punch collects its scientific data in the shadows of these ingenious baffles. We've practically eliminated all stray light. The shadows are 10,000 times darker than the darkest night sky. Each of the 4 Punch cameras in Earth orbit is outfitted with polarizing filters, similar to the lenses of common, everyday polarized sunglasses. These filters help Punch measure how strongly polarized the scattered sunlight is. The constellation of Punch spacecraft work together to build up one large image every few minutes.
And that's how Punch is able to observe the polarized light of the sun's outer corona together with the solar wind of the entire inner heliosphere as a single, unified system.
And that's why Punch stands for the Polarimeter, to unify the corona and heliosphere.
Solar storms can leave the sun in any direction, and Punch is able to observe them all.
Returning back to Earth, we join a group of teachers who are collecting data in the shadow of the moon during a total solar eclipse. They are working on a science project called Citizen Kate 2024. Just like Punch, the Kate 2024 setup measures the polarization of light from the solar corona to track structures forming and evolving there.
We can compare the Kate and Punch fields of view on the sky. Here we see the size of the rectangular Kate field of view relative to the totally eclipsed sun. Punch observations start farther out in the corona. Now we see the circular field of view of the Punch Unify coronagraph and the square fields of view of the 3 Wiffi spacecraft.
The outreach program embedded in the Punch mission encourages everyone to become sun watchers. You are invited to strengthen your sense of connection to the sun through your own direct experiences of solar beauty and wonder, through the grateful hearts of your sky-watching ancestors, and through the eyes of extraordinary NASA missions like Punch and Parker. All of these perspectives help to advance our awareness and understanding of how the sun touches humanity.